Problem 11. Evaluate the integral of x to the fourth plus x squared all over x to the fourth dx. All right, even though there's a denominator on this one, we're not going to do a du over u just because there's so much going on in the numerator. So what I'm going to do instead is bring the x to the fourth up top. And that's going to make this x to the fourth plus x squared multiplied by x to the negative 4. Okay, now I'm going to distribute. When I do this, we're going to add the exponents. So 4 plus negative 4 would just be x to the 0. Plus this one 2 plus negative 4 would be x to the negative 2. Okay, x to the 0 is just equal to 1. So we're going to have the integral of 1 plus the integral of x to the negative 2. The integral of 1 is x. And then the integral of x to the negative 1, I'll increase my power by 1. So it'll be x to the negative 1. And then the reciprocal goes out front. So rewriting this, this would be x minus 1 over x plus c. Okay, problem 12. Evaluate the integral. The integral from 1 to 5 of the absolute value of x minus 3 dx. Okay, there's a couple different ways that we can work this. I'm actually going to work this the picture way first. We know that the absolute value graph looks like a V. The minus 3 is going to shift the graph to the right 3 places. So shift it to the right 3 places. It's just going to look like a V. Okay, we would like to find the area under the curve from x equals 1 to x equals 5. So from x equals 1 all the way over to x equals 5. So finding the area under the curve, you'll notice I just have two triangles. I'll call them triangle A and triangle B. Okay, the first triangle is 1/2. The base of that triangle, it's easy to see that it is 2 spaces. And then the height, if you're not sure what the height of that is, we're going to plug, since it's occurring at x equals 1, plug 1 into this problem, and you'll notice we'll end up getting 2 as my answer. So the height is 2. So the area of triangle A is 2. Okay, and then triangle B is again 1/2. The base is still 2. And then the height is occurring when x equals 5. So again, if I plug 5 into this problem, I will end up once again getting 2. And so the area of that triangle is also 2. And if I add those two together, I'll get 4. So that is one way to approach the problem. The other way is to split this integral up into 2 parts. And to figure out where it splits, we're going to set x minus 3 equal to 0, which means it's going to split at x equals 3. So we're going to take the integral from 1 to 3 of x minus 3 and add it to the integral from 3 to 5 of x minus 3. And on this one, I'll put a negative because we need to bump this back up because naturally it will end up underneath the x-axis. Okay, so now if I take the integral of this, I'm going to get 1/2 x squared minus 3x, but this negative is going to make this negative and this positive, and then I'll evaluate it at 3 and 1. So if I plug in 3, I'll get negative 9/2 plus 9, and then minus negative 1/2 plus 3. So when I figure that out, that will give me, let's see, 9 minus, this will be 18 halves, minus 9 halves, that will give me 9 halves, minus, this will be 6 halves, so negative 1/2 plus 6 halves will be 5 halves, and 9 halves minus 5 halves is 4 halves, which is 2. Okay, so that part of the problem is 2. Now we're going to do the same thing over here. The integral of x minus 3 is 1/2 x squared minus 3x. I'm going to evaluate it at 5 and 3. So if I plug in 5, I'll get 25 halves minus 15. And then minus, when I plug in 3, I'll get 9 halves minus 9. Alrighty here. This will be 30 halves. So 25 halves minus 30 halves will give me negative 5 halves minus, let's just change this to 18 halves. 9 halves minus 18 halves will be negative 9 halves. Change those to pluses. Negative 5 halves plus 9 halves will be 4 halves, which is again 2. And then when I add 2 plus 2, I will end up getting 4. Problem 13. Okay, on this one, we would like to, we know that f of x is equal to the integral from 4 to 5x of t squared minus 2 sine t dt, and it asks us to find the derivative, okay? So it's asking me to find the derivative of both sides, okay? So if I find, as long as this is starting with a constant, which it is, I can use the second fundamental theorem of calculus, which basically just tells me if I take the derivative of an integral, the derivative and the integral sign cancel each other out, but we're going to put the 5x wherever I see a t. So it's going to be 5x quantity squared minus 2 sine 5x. And then I'm not done with this because I do have to use the chain rule here. If this is not just x, we're not done until we multiply by the derivative of 5x, which is 5. So now cleaning this up, I'm going to get 25x squared minus 2 sine 5x all multiplied by 5. And we could work that out one step further, or I'm just going to leave it with the 5 in there. Okay, problem 14. We would like to evaluate x sine of x squared dx. My hint for you is whenever we just have one trigonometric function in our integral problem, we're always going to let u be the exponent. So I'm going to let u be the exponent. So u will equal x squared. If I take the derivative of x squared, that will be 2x dx. I notice I have the x, but I'm missing the 2. So to undo that, I'll do a 1/2 on the outside. So I'm going to have 1/2. I've done nothing with sine, so sine stays in my problem. X squared I called u, and 2x dx I called du. Okay, now from here, we just need to know our integral rules at this time, and if you don't, do some studying of them. The integral of sine is negative cosine of u plus c. And then that problem is done. All right, problem 15. The graph of f is shown, and we know that p of x is equal to the integral of f. And just a note, negative 2, 1, this should be negative 2. Negative 2, 2 should be negative 2, 1. So just make that note on your paper. Okay, what I like to start out by doing, we know that p, because it's the integral of f, is going to be the area under the curve. Okay, p prime, if I take the derivative and the integral, they just cancel each other out, so it will just be the curve. And p double prime will be the slope of the curve. So that should help me out. Okay, if I'm looking to find p of negative 2, I'm going to go right up into here, and we're going to plug negative 2 in for my x. So it's going to be the area under the curve from 1 to negative 2 of f. Well, I'm not allowed to go from 1 to negative 2, so it's going to be the opposite of from negative 2 to 1. So if I'm going from negative 2 all the way till I get to 1, notice that I end up with a half circle and then a triangle. So I'm going to get negative, okay. Half circle is going to be 1/2 pi r squared. The radius of this circle looks like it is 1, so it's going to be 1 squared. Well, I won't even do that yet. And then plus this is a triangle, it's going to be 1/2 times the base is 2, times the height is also 2, but since this area is below the x-axis, it's going to be negative. So I'm going to get, keeping this negative sign out front right now, it's going to be 1/2 pi minus 2. Okay, and then since we've got the negative out, this will actually be negative 1/2 pi plus 2. Okay, to get p prime of 3, we're just going to look at the curve at 3. So at 3, my answer will be 4. And then p double prime of 4 will be the slope of the curve at 4. So at 4, 1, 2, 3, 4. At 4, you'll notice my point is right on this line, so we just need to find the slope of that line. So the slope of that line will be 1 minus 4 over 5 minus 3. That gives me negative 3/2. So p double prime of 4 would be negative 3/2. Okay, find the x-coordinates of all relative minimums of p. So if I want relative minimums of p, I need a p prime chart. And p prime chart is the curve. So I'm noticing that the curve is equal to 0 at negative 3, and then at negative 1, and then at 1, and that is it. Okay, before negative 3, my curve is above the x-axis, so p prime will be positive. Between negative 3 and negative 1, my curve is still above the x-axis, so still positive. Between negative 1 and 1, my curve is below the x-axis, so p prime will be negative. And after 1, p prime is above the x-axis, so it will be positive. Okay, if I want a relative minimums occur where the p prime changes from negative to positive. So it looks like at x equals 1 is the only spot. So x equals 1 is a relative minimum, and that is because p prime changes from negative to positive. All right, and then it says find where P is concave down. Concavity has to do with P double prime, so let's make a P double prime chart. We're looking at the slopes of the curve. So the slopes are negative, because the graph is going down till I get to -3. And then my slopes are positive, because the graph is going up till I get to -2. Negative, positive. And then the slopes are going down all the way till I get to x equals 0. We don't really care that there's something happening going on there. And then after that, the slopes are positive until I get to 3. And then the slopes are negative after that. So if I'm looking for where P is concave down, it would be here, here, and here. So at the beginning of my interval, which will be -4, till I get to -3. And then again from -2 to 0. And then again from 3 to the end of my interval, which is 5. That's all the places where P is concave down, and that would be because P double prime is negative.